Hi everyone to take 2 of homework 1 part C, and we're going to be doing C1. As C2 I will be in front of a chalkboard deriving the problem for you. But before we get into that, so C1 is the question is explain while implementing the Python code to obtain the Anton coefficients for water by nonlinear regression of the vapor pressure data at here. So when here, this is what the data looks like in its raw form. And let's get to coding it in. So first, we need to load the text in, which is, before we need to do that, actually, we need to get our file. So our file is here. And here we go. You save it, and then you save it back. So we load text, which equals, don't even need equals. It's going to be the name of the file. And then the delimiter, which is what's separating these files. Or what's separating these, what's separating the files, which would be a comma. If this, I did not put CSV. Okay, that looks good. Now let's go over here and just check. So we got there and there, so that's good. So now we need to actually put this into a location. So we're going to call this P data equals that. And now we need to unpack our files. So we're going to have T, comma, P experimental equals P data dot T, otherwise known as transposing our array. This is because Python reads its files from left to right for the same variable. So for example, this would be the temperature is only here. And then it just break everything. So we want to do that there. Now we can check for T. We get 293, 303. You can go and check 293, 303. These are good. Those are right. All right. So yeah, there we go. So now that we have our values, we can start to put them into an equation. So we're going to define we're going to calculate our model and then the error between that model and our experimental data. So we're going to define our SSE1 as a vector. And we're going to do A, comma, B, comma, C as, here, let me put this up real quick. This is the equation we're going to be using today, where T stands for temperature. So this equals a vector. And now we're going to do our model equals 10 to the power of A minus B divided by C plus T. And so from here, we can return, so we want the sum of our error and so we're going to be doing our model minus our P data, or P experimental, as this solves for pressure. And we are going to then square this as to make sure there is no negative. Okay. And it's not broken. So this is good. So now let's just test something real quick. We have 10 to the power of, let's say, 6 minus 1. Let's do 8. 8 minus 1 divided by we're going to say temperature is 0. So we're just going to do, or C0, so we're just going to do 373. And that should equal close to 100,000 more atmosphere. So this is good. It means what we have so far should be right. So now that we have this, we are going to try and minimize our function. So minimize SSE1, and we're going to try and, so what we're doing is trying to find where this is 0, or where we can find our values. So now we're going to have guesses for our values. So I'm going to say 8, comma 1, and we're going to have C as 0 as above. And let's hope this works. Okay. So it says here that the desired error is not necessarily achieved due to precision loss. And we have some of our numbers. But what this means is, as we're going to the power of 10, as our numbers get bigger, so does our final value. And when things get from 10 to any power, it starts getting big very fast. And so that can affect our error. This is homework 1, part C2, in which I'm going to derive our matrix for us, for our linear regression. So what we start off first is this is what we start off first, and it equals the pressure. It equals the pressure we have in our data. And so first what we would need to do, as we did earlier, is we're going to take the log of this. And when you would take the log of this, you will get and it really depends when you see we have log p equals a minus b divided by t plus c. And in our work, we decided that c would be 0. And that was easier, so we would be able to derive an equation on the fly. But what we're doing now is we're going to need to account for all of our variables, as c will not always be 0. And so to do that, I am going to make I'm going to distribute t over c, or t plus c. And this ends up looking like, we have, here real quick, yep, we have log p t plus c equals a t plus c minus b. And, oh gosh, my handwriting is horrible. But here, let me make it somewhat legible without this in the way. So parenthesis, this is an addition sign. And so here, let me rewrite this again, as I'm trying to make sure it's legible so you're able to see on this very chalky whiteboard. And so we're going to keep this over here, and we're going to factor it out. So we get t log p, which we like, as we actually already know these, as these are in our data. So this is a no-brainer for what we're going to use. And that then we have add to t log p AT plus AC minus B, and there you go. And now we want T log P to be on a side all of its own, because we know those variables. Everything else either has an A, B, or a C involved. And this means we can have our answer, and we can derive our equation using our matrix, as I hopefully try to stay in frame. So we get T log P equals AT plus AC minus B excuse me, minus C log P. And let me erase our bottom term real quick so we can start working with this, or at least figure out what we're working with. So what we have here is T log P, which are both known, equals AT plus AC minus B minus C log P. And from here, we can work and design our matrix. And so what we have here, AT. So we have T, T1, in which there would be a long line of T's. And then for our variables, we would have A. Okay, now what else do we know? We know this. And so next is going to be negative log P. As you don't want to make a variable a negative when you don't have to, especially when coding. In which again would be another long line of negative log P1, P2, P3, etc. And so then we have C, and we have this term here. And this term is scary. It's scary because it is 3 unknowns. And so what we would do is, if you realize the coefficient of all of these is 1, we are going to have a long line of 1s. And that equals D. Because if it helps us calculate A and C, we should be able to calculate B, no problem. And all of this equals T log of P. Etc. And you work through this, and it's hard once you start working with it to figure out where it's going. However, once you start deriving it, you kind of start to understand, okay, we have this variable, how do we move on to the next? Or we need this, and we have this. How can we mathematically derive or mathematically create a problem for us to solve? And so here, now that we have, let me erase real quick, now I have more room to write. As my math professor in this room likes to say, we have this. Don't look at this. The only other one, look at this. So, sorry about that. I lost my train of thought. However, what we get here is we're going to call this array A. Let's write that bigger. We're going to call this array V for variables. And because we're missing B here, I think we're going to call this B. Let's call this array B. And so if we want to calculate, our variables, what we need to do is solve for it. And to do that, you would multiply by our transpose. So that's designated as A dot T. Sorry, that is very bad writing. A dot T at A, and then we would do comma, because if you have two of them, you are able to calculate the other. Comma, and then you also multiply this by A dot T. And we actually know what B is, so it would actually, this would end up being A dot T, okay, at A, and I'm drawing the ats because in co-laboratory, the at is when you is the sign for multiplication with arrays. At A, comma, actually B or ABC, comma, A dot A's transpose multiplied by T, T1, then log B1. And what this ends up giving us, when you plug it in and everything pops out perfectly, you end up receiving an A value, a C value, and a D value, which you can end up plugging back in for B. And I think that will be all for this. Thank you for watching C2, and I hope you like the rest of the video. Hi everyone, this is homework 1 part C, C3, and it asks us to please explain while implementing the Python code to obtain the Antoine coefficients you use in our multilinear regression approach, or basically what it's asking us is to code our design matrix we just derived in C2. So first, what we need to do is start with A. So A equals P dot C underscore, and then we have, I'm not sure if it's brackets, we can figure that out. I'm going to say no for now. Actually, no, it is. T for the temperature, and then we have negative log exponential, and we have ones like T. Okay, nothing broken yet. It's a good sign. So now let's plug in our variables and for the full matrix. So we have A, comma C, comma D equals NP dot lin alg, and we're going to solve, as I haven't taken this class, or linear algebra solve. So now from there, it is A dot T, and we're going to transpose of A, multiply by A, comma, remember we've done this already, times the transpose of, then multiply that, the temperature times the log pressure exponential. And it's okay. So now let's check for, make sure D isn't an array. Okay, that's good, it's not. So we have D, or sorry, B equals A times C minus D. And B, okay, there we go. We get B to be basically 1,772. And that concludes what we're going to need to do. Thank you.